I do not sound like a bumbly idiot. Quiet. Let me do my lesson.
All right.
All right. So today we're going to do discussion 4-2, polarity and intermolecular forces. I'm going to try to do it without any snarky comments from my wife. Okay, so when we talk about polarity, we're going to be talking about two kinds of polarity. The polarity of bonds and the polarity of molecules. So let's first focus on bond polarity. All right, so polarity is just the existence of oppositely charged ends on a bond or a molecule. And all that means is that the bond or the molecule will have a positive end and a negative end. And to measure polarity, we use what are known as dipole moments. Now, dipole moments are just vector arrows that show the amount and direction of charge in a dipole. So the vector arrow and a dipole moment will always point toward the negative end of the molecule or the bond. If you're unfamiliar with vector quantities, just ask me about it in class, because I'm sure most of you learned about that in physics. All right, so in a polar bond, electrons are shared unequally between the atoms. And in a nonpolar bond, the electrons are shared equally. So I kind of like to think in bond polarity of that sharing of electrons being like a tug of war. And the two atoms involved in the bond are both pulling on the electrons. Now, the atom that is better at pulling on the electrons will have a greater share of the electron density. So the property used to determine bond polarity is electronegativity. And the more electronegative atom will have a greater share of the electron density. So that means if you were going to draw a vector to show the dipole moment in a certain bond, that vector would point at the element that has a higher electronegativity value. All right, so molecule polarity. Now, if your molecule has ionic bonds, then the type of molecule you're going to get will always be an ionic compound, and we'll explain that in a minute. Now, if you have nonpolar covalent bonds, you'll always have a nonpolar molecule. The reason it'll be nonpolar is because there aren't any dipole moments associated with the molecule, so there couldn't possibly be an overall dipole moment in the molecule itself. And if you have polar bonds, you can have either a polar or a nonpolar molecule. Or the molecule will be polar if there's a net dipole moment. In other words, when you add up all the vector arrows, if they don't all cancel each other out, the molecule will be polar. You'll have a nonpolar molecule if all those dipole moments cancel out. All right, so shapes and polarity. Now, certain shapes will always be nonpolar as long as all of the atoms around the central atom are the same. These shapes are linear, trigonal planar tetrahedral, trigonal bipyramidal, octahedral, and square planar. Now, if we look at all those shapes, they all have a very important thing in common, except one of them. And that is the absence of lone pairs on the central atom. Please recall, in the square planar shape, there are 4 bonds emanating from the central atom, all in the same plane. And there will be 2 lone pairs of electrons on that central atom, both above and below the plane of the bonds. All right, now again, it's important to note this is not true if there are different atoms around the central atom, because those atoms will then have different electronegativity values. For example, methane is nonpolar because all the carbon-hydrogen bonds are equivalent, and so in that tetrahedral geometry, all the dipole moments will cancel each other out. But if you replace one of those hydrogens with a chlorine, which has a much greater electronegativity, you'll have a net dipole moment pointing toward chlorine in the bond. Okay, so these shapes will almost always be polar, bent, and trigonal pyramidal. Now, the only time these shapes will produce nonpolar molecules is if the bonds are nonpolar. Okay, so if the bonds are nonpolar, you'll still get a nonpolar molecule because there aren't any dipole moments to cancel out. All right, so let's look at some examples. I will do the first 2, and then I will have you guys do the second 2 to determine whether these are polar or nonpolar molecules. Now, with water, we know that those oxygen-hydrogen bonds are definitely polar bonds. And if you look at the electronegativity values, oxygen has a much higher electronegativity value than hydrogen. So we'll have a pair of dipole moments pointing toward the oxygen atom. Now, when you add those 2 vectors together, you get a resultant vector which will point directly toward the oxygen atom. Now, the links here are not, the links of the arrows are not to scale. I'm just kind of giving you the idea. Now that will impart a partial negative charge on the oxygen atom and partial positive charges on the hydrogen atoms. Now, to represent a partial charge, we use a lowercase delta with a plus sign or a minus sign. Now, since these are not ions, they don't have permanent charges or full positive and negative charges, but because there is a greater share of the electron density closer to oxygen, it will have a partial negative charge. So that means that this molecule is a polar. Now, if we look at carbon dioxide, each of those carbon-oxygen bonds is indeed a polar bond. But if we add those two vectors up, since they're the same length approximately, and pointing in opposite directions, they will both cancel each other out. And so there's no net dipole moment, and the molecule will be nonpolar. So take a moment, pause the video, and draw the dipole moments around nitrogen-hydrogen bonds in ammonia and around the carbon-chlorine bonds in carbon tetrachloride, and determine whether or not those are polar or nonpolar molecules. Okay, so in ammonia there are 3 dipole moments along those nitrogen-hydrogen bonds, all pointing in the direction of nitrogen. So there will be a net dipole moment going toward nitrogen, which will make the nitrogen partially negatively charged and all the hydrogen atoms partially positive charged, which makes this a polar molecule. Now again, in carbon tetrachloride, all the carbon-chlorine bonds are very, very polar, but since they're all equal length and pointing in opposite directions, you get an overall molecule that is nonpolar. Again, tetrahedral, all the atoms on the outside the same, so nonpolar. Alright, so a molecule's polarity will determine its intermolecular forces, and thus its properties. Remember, intermolecular forces are the forces between molecules that hold them together. So examples of properties affected by polarity and intermolecular forces are the melting and boiling point of a substance, the substance's volatility or its tendency to evaporate, and thus its vapor pressure, surface tension, and viscosity, which is essentially how thick a liquid is, or its resistance to flowing, or its anti-flowiness, if you want to be really scientific. All right, so let's look at all the types of intermolecular forces one by one. So the definition of ionic bonding is electrostatic attraction between oppositely charged ions. Because ionic bonds are formed by the transfer of electrons, which creates cations and anions, the cations and anions just stick together by nature of their mutual attraction to the opposite charges. Now these forces are very, 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 very strong, and it explains why all ionic compounds are solid at room temperature and why they have extremely high melting points. The next is dipole-dipole forces. Now, dipole-dipole will occur in molecules that have a permanent dipole moment. In other words, the dipole moments don't cancel out. So basically, dipole-dipole, believe it or not, happen in polar molecules. And examples of that would be chloromethane. Again, there's a net dipole moment pointing toward chlorine, and in propanone. Okay, now hydrogen bonding is a special kind of dipole-dipole interaction where a molecule will contain a hydrogen atom bonded to either nitrogen, oxygen, or fluorine. So good examples of this are water and ammonia. Now, hydrogen bonding is a much stronger type of dipole-dipole bonding than standard dipole-dipole bonding, so it deserves its own special category. The next is London dispersion forces. Now, London dispersion forces are weak, and they're caused by temporary forces that occur between very quick shifts in the position of electrons. Well, what that means is that electrons are constantly moving around the outside of molecules. They're zipping all over the place. And if the electrons happen to be on one side of the molecule at any given point in time, then the electron density will be centered on that side of the molecule, and it'll give it a temporary negative charge. Now, because the electrons move around so quickly, those temporary dipoles only last for instant moments in time, and so they're not permanent, and they're very, very weak. All right, so dispersion forces occur in all molecules. That means if a molecule has hydrogen bonding is just the strongest intermolecular force, but it also will have London dispersion forces. All right, now London dispersion occur in all molecules, but they are the strongest and only intermolecular force present in nonpolar substances. So these substances will be volatile, they'll evaporate very easily and have low melting and boiling points, and they'll also have low surface tension. I'll do a cool demonstration on what we mean by surface tension in class. All right, now van der Waals is kind of an old school term that really doesn't get used that much anymore, but the IB still makes us teach it to you. Now, van der Waals is just an overarching term that encompasses dipole-dipole, dipole-induced dipole, and London dispersion forces. So it's basically just all the intermolecular forces except hydrogen bonding. Now, dipole-induced dipole forces are formed when polar molecules come in contact with nonpolar molecules. Now, when that happens, the positive end of the polar molecule can actually draw electron density from the adjacent molecule, creating a slight dipole moment. And the negative end of the polar molecule can actually repel the electron density in the adjacent molecule, creating a slight positive charge on the end of the nonpolar molecule. So these are not dipoles within the nonpolar molecules. They're dipoles that are caused by interacting polar molecules. Sorry, that was a little rough sounding. All right, so how do we know if two substances will mix? Well, we all remember the rule like dissolves like. And that says that polar molecules will only mix or dissolve in polar molecules or polar compounds. And nonpolar molecules will only mix with nonpolar molecules. This is exactly why when we did Lab 2-3, the hexane layer, when we mixed the hexane layer with the halide salt solutions, the hexane layer sat on top. It did not mix in because the two are not soluble in each other. It's also why oil and water don't mix. All right, so molecules that have strong intermolecular forces will have higher melting and boiling points. And the reason why is because melting and boiling is essentially separating molecules. Molecules that were previously connected by these intermolecular forces are separated. And so the stronger the intermolecular forces are, the more difficult it is to separate them. All right, so here's an example of that. If we look at these different substances, we can compare their intermolecular forces with their boiling points. So sodium chloride is an ionic substance. So we see that it has a boiling point, or melting point, actually it's a boiling point, of 1,465 degrees Celsius. Very, very, very high. Now water has hydrogen bonding, and its boiling point is right around 100 degrees. Now if you look at H2S, H2S has the same bonding structure as oxygen, but because the hydrogen and sulfur bonds in H2S are nonpolar bonds, that means the strongest intermolecular force is dipole-dipole, and so the boiling point is lower than room temperature at negative 60 degrees. And for carbon dioxide, another nonpolar substance, it is also even lower below room temperature at negative 78.5. So we just separate down here H2S and water to show the difference. Hydrogen bonding produces a much higher boiling point than does London dispersion forces. All right, now there's some other factors that can affect melting and boiling point. A great example of that is the halogens. Right? So if you look at the halogens, fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Now these are all nonpolar covalent molecules, so they all have weak dispersion forces between them. Right? But the larger molecules will have a higher melting and boiling point, and that is due to the size of the electron cloud. Now the larger molecules will have a larger electron cloud, they just have more electrons. So there's more electrons zipping around creating those temporary dipole moments. Right? So the larger the electron cloud, the stronger the overall dispersion force will be, and so that is why iodine is a solid, whereas fluorine is a gas. All right, now comparing IMFs and organic compounds. If we compare the IMFs between ethane, ethanol, and ethanoic acid. Now, it's really important to note that intermolecular forces are additive. In other words, when you look at a molecule, you have to combine all the different intermolecular forces that we have in the molecule. So if we look at ethane, these are all nonpolar bonds, and so this is a nonpolar molecule, so it has London dispersion forces. Now if we look at ethanol, ethanol has oxygen bonded to hydrogen, so it has hydrogen bonding. So we would expect the boiling point of ethanol to be higher than that of ethane. If we look at ethanoic acid, ethanoic acid also has the hydroxyl group giving the hydrogen bonding, but it also has a carbon-oxygen bond here giving an additional dipole moment in the molecule. So when you look at the boiling points, the boiling point of ethanoic acid will be greater than the boiling point of ethanol, which will be greater than the boiling point of ethane. And if we compare the intermolecular forces in ethanol, pentanol, and hexane-1-ol, oops, I actually left ethanol off my animated PowerPoint, but you know what it looks like. It's right up here. Right? Now, all three of these alcohols have a hydroxyl group at the end of the molecule, but as we increase the length of the chain, we actually are increasing the total amount of London dispersion forces between those molecules. So again, you will see the boiling point increase as the molecules get larger and larger. All right, and just a couple of practice questions. Take a moment, pause the video, and see if you can work these out, and then we'll be all done. Let me sip my seltzer. All right, so which compounds form hydrogen bonds in the liquid state? Now, in order to form hydrogen bonds, you have to have oxygen, nitrogen, or fluorine bonded to a hydrogen atom. So if we look at choice D, we have nitrogen in the molecule, but the nitrogen atom is bonded to 3 ethyl groups. So it's bonded to 3 carbon atoms, no hydrogen. If we look at choice C, that is an aldehyde. So the carbon, there is oxygen and hydrogen, but both the oxygen and the hydrogen are bonded to the carbon atom and not to each other. In choice B, we don't even have any N, O, or F, so that's not it. And in choice A, we have an alcohol. We have the hydroxyl group at the end of the alcohol, so that is the correct answer. And finally, which pair of compounds is arranged in correct order of relative boiling points? Well, again, let's start up from the bottom. So we have ethanoic acid and ethanol, and once again, they both have the hydroxyl group, but ethanol also has that carbonyl group as well, so we would expect the boiling point of ethanoic acid to be greater than the boiling point of ethanol. If we look at choice C, hydrofluoric acid, or HF, has hydrogen bonding, and HCl has dipole-dipole as its strongest intermolecular force, so again, we do expect the boiling point of hydrofluoric acid to be greater than that of hydrochloric acid, excuse me. If we look at choice B, we have ammonia. Now, ammonia has nitrogen bonded to hydrogen in 3 different places, so it also has hydrogen bonding. If we look at phosphorus trihydride will have dipole-dipole, so we would expect ammonia to have a higher boiling point. And if we look at choice A, we have H2S, which has London dispersion forces due to the nonpolar sulfur hydrogen bonds, and water has hydrogen bonding, so it is lined up correctly. All right, and that's it for discussion 4-2. If you have any questions, bring them to class. Thank you for listening.